Okay, we've got 1:30, so why don't we get started? Good afternoon, Research Methods.
Good afternoon.
Welcome to Wednesday of week number 15. A couple of announcements today. As you can see on our syllabus, we have a computer quiz coming up. Have a big announcement about that, though. Some good news and some bad news. The good news is this. Back in September, one of the provosts contacted me and asked me if I wanted to apply to the University of Chicago, where there's a conference on using technology in the classroom. She knew that I was doing video lectures. So she said, Nestor, I think the University of Chicago would love to hear from you on that. So I applied, and I hadn't heard anything back until early this week when I found out that actually it's been accepted, which was the good news. The bad news is, thank you. That was not an attempt for cheap applause, but thank you. The bad news is that the conference is on Friday, when our computer quiz is going to be. Oh, so sorry to disappoint. So, unless there's tremendous objection, I guess we'll just cancel the computer quiz. It won't happen. Okay, just won't happen. I've got to go to the conference. So this is what I was thinking about doing. There are 50 points on that quiz. There are 800 points for the semester. I thought we'd just rearrange things so that we make the semester out of 750, and these 50 points just go away. It doesn't help you. It doesn't hurt you. It's a non-issue. Okay? And what we'll do is we'll continue to practice today as if the quiz were coming up. That way, if a question that might have been on the quiz winds up on the final exam, you're not caught cold, but we just don't do the quiz. Now, I could have moved the quiz to a different day, but we're actually running out of days really soon. And we also have, coming up next week, we have an article analysis due. And I didn't want to have you do a quiz and an article analysis on the same time. I didn't want to move it to Monday because I realized some of you have tests or other things on Monday. So I think it's just simplest to cancel things. Yes, please.
So then do we not have class on Friday?
You do not have class on Friday. You can show up if you want, for old time's sake, but I won't be here. I'll be in Chicago. So, talking about video lectures. I'll be talking about video lectures. By the way, my audience, you might be interested in this. My audience is going to be people who are just a couple of years older than you. They're bringing together faculty from around the nation who are using technology in psychology classes. And we're going to be talking to University of Chicago faculty and graduate students who have gotten into their psychology graduate program. They're a couple of years older than you, maybe just 1 year older than some of you. And so we'll be talking about that. Yeah, please. I would imagine that there are. The other folks who are coming are from all around. I think I'm the only Denisonian who's going to be there this time. But I did notice that there was somebody from Kenyon on the list, somebody from Kenyon in the foreign languages, who uses some other kind of technology for foreign language acquisition. Folks from Macalester, usually they're from smaller liberal arts colleges like ours. So I'm looking forward to it, but no computer quiz. Oh well. All right, so we'll do it that way. If it's okay with you, we'll make the course out of 750 points rather than out of 800 points. That doesn't raise your score, that doesn't lower your score, it just makes the thing a non-issue. Okay? But at some point in the future, you might want to know how to compute regressions or other kinds of things, so why don't we practice that today? And then after today's session, we'll just see you on Monday. Okay? And then we'll just take the semester through just like it would have been scheduled. The only thing is that computer quiz is off the charts. Okay? All right. All right. Thank you for bearing with us. Thank you for the greater good of promoting education. So appreciate your doing that. Okay, why don't we do it this way? Why don't we have you join us inside of Excel? We're now going to work on the topic of regression. This is what we did yesterday in class. And if you'll join me out on the S drive, you know that we go to our 203 course, and then we go into resources, and we have practice problems. One new set of practice problems would be called regression problems. And when you go into regression problems, there's going to be an Excel spreadsheet. That'll be the one that we practice on today, and it says regression exercises. Same kind of setup that we have throughout the semester. We have something like 5 different problems here. There's a color-coded answer key next to each one of these. We'll go through. How many people have the formula sheet from yesterday? Okay, why don't we start working on this? It's pretty straightforward. So we're going to find the equation for the best fitting line. Let's all yell out, what's our favorite equation? Y equals mx plus b. We can't get enough of that this semester. Okay, right? So we're going to find the equation for the best fitting line in this data set. And if you open it up for problem number 1, you'll see some familiar variables. We have college GPA, high school GPA. Okay? I've made mine a little bit on the big side so that people in the back can see it. If you need to shrink it down, you can go to View and you can zoom in to different levels. I'm going to leave mine there so folks in the back can see that. Can the folks in the back see that? Is that working for us? Okay. All right. So we're getting pretty good at these computations now. So maybe I can play like I'm naive about these things and you can just yell out instructions to me. So if I wanted to begin computing this, and this were my data set, and I were going to be evaluating these kinds of hypotheses, the null hypothesis in the population, there's no correlation between high school GPA and college GPA. Okay, that's the null hypothesis. We'll use a regression analysis. What might be a first step for this data set? Yell it out, Kip. Okay, why don't we take the means of both data sets? So actually we have, I'm just eyeballing it, we have 32 people who have participated in this hypothetical study, and we have a college GPA and a high school GPA for each. So 32 pairs of scores. Kip is right, we'll have to take a mean. What's my syntax? Yell it out. Equals average, okay? And then we do equals average, we highlight over the GPA portion. We close that off. And I will call that, for example, my mean x. You wouldn't have to do it that way, but it just might help you. In the not too distant future, we're going to be needing to grab the mean for x and the mean for y. And just to make sure we're all on okay on that, who gets 3.3125 for their mean, okay? If you like, we can actually steal that with a control C and a control V over here, and we'll just change mean x to mean y. But we copied these spatial relationships, copied that genotype, and we get now a mean for the y values, which would be the college GPA mean, and I get 3.1938. Who can confirm that number? Okay? How are we doing? So far it looks like everybody's on board. Okay? All right, that was a really good start. We have the means, so this is going to be a parametric test. Just by way of review, that means that we've got averages going on here. Okay, what might be another good step from this point? Go ahead, Jenna. We have to find the deviance? Okay, all right. So let's see if we can do that. Maybe we'll go to the top row, or at least row 4, and we'll put in something like S minus M, which corresponds to a score minus its mean. So I'll say equals. I'll click on the neighboring 2.5, and I will subtract from that using the minus key. I'll dial down. I'll click on 3.3125 for its X score, and I get a negative 0.813. Who's got that? People confirming that? Okay. Now I'm going to make an error. Well, I've got that one. Why don't I just copy that one on down? No. Why not, Natalie? I have to freeze the cells, right? Otherwise, I'm going to be copying an inappropriate spatial relationship. Can we all yell out how I freeze the cells? Dollar signs, okay? And I really want to freeze the one that was the mean x. That's the one that I have to subtract from each of our scores. So I'm going to put in a dollar sign before the B, the second of the two B's, and before the 38. The first dollar sign freezes the column B for that cell. The next one, the row 38. Okay? All right, and then if I do that, I'm still back to my minus 0.813, but now if I drag down, I've got all that. Okay? Just out of curiosity, something we haven't mentioned in a while, if I were to take a sum of these, any idea what that might add up to? A sum of these deviates? You have an intuition about that? So from all these scores, we took away the mean, which is the center score. What do you think the deviates might add up to? The mean might have been a good guess. Why don't we see what this adds up to, at least approximately? We actually wouldn't have to do this, but since we're a little bit ahead of the game, we can develop some intuitions about this maybe. I'll go back over here to home. I'll click on my summation. Oops. Equals sum. And I'm going to sum over the deviates. And that's approximately 0, right? Within rounding, there are 16 zeros before we get to that 4. Okay? Who's following that? Okay, that it is 0. Who finds it intuitive that it's 0? Do you want to help us out with why that's intuitive?
I said 0 only because there are so many.
Okay, if they were all negatives and we added all the negatives, it wouldn't be 0. But if it's a mixture of negatives and positives, with some of them being very, very strong positives, very far away from the mean on this side, some of them being very strong negatives, those will tend to cancel. Others that are modestly negative will cancel with those modestly positive. Who's okay with that? All right, really good. So by the way, that was just a little aside. The deviates themselves would add up to 0. So we need some way of getting around that problem. What might our next column be? Okay, we're going to take the same idea, that s minus m that we just had, and we'll square that. That'll turn everything positive, and that will get us away from 0. So equals my neighbor to the left quantity squared. And then I can drag that genotype down. Okay. And I will go ahead and take a sum of that. And I'm getting the sum of the squared deviates. And I wind up with a 3.635. We'll let you catch up. When you get that number, can you confirm by raising your hand? Okay? And I'll label that as SS, sums of squares for my x variable. Okay? And I'll save that much. Okay? Okay, why don't we go ahead and do the same thing for the y-axis variable, which is the college GPA. That would be the item that we're trying to predict. Okay, x is our predictor variable. This is our criterion variable. Okay, so let's go ahead and step on through that. Equals the 2.9 minus its mean, and its mean is the 3.1938. Okay, and of course, as I think it was Natalie pointed out, we want to freeze that by putting in the dollar signs. And we might also want to square that. And we can pull those on down when we're set. Okay. We'll let you plug away on that. I'll just change my labels over here. We wind up with the sum of the squares for y, which is college GPA. And when you get that far, if you get to 4.2788 as your sum of squares for y, can we raise it? Okay, so most of us are there, but some of us are still plugging, so we'll let them catch up. Okay. The sum of squares for x, as you'll see in here, is going to be some indication of how far we are running on the x-axis. And we'll have to do just a little bit more computation to figure out how far we are rising on the y-axis. But we're not quite there yet. We'll let a few folks catch up. Okay, show of hands. Who's got 4.2788 as the y? Anybody lost? Lose anybody on that one? Okay. All right. So now we're looking at this same formula. Anybody want to suggest a next step? Next step? Thank you, Jenna. Okay, good. Okay, you want to multiply the deviates. If I can have your attention just for a moment, this is almost always where I lose a student. We've done this before. I think green was my lucky color the last time, so I'm going to use green. The deviates, again, are the s minus m's. They are not the squared deviates. We want the regular deviates, and Jenna pointed that out correctly. So we're going to look at the x minus x bar column. I'll make that a different color. Green was my lucky color last time. I'll make that green. I want to multiply those guys for my high school GPA. Those are my high school GPA deviates from the mean by their counterparts over here for college GPA. I'll make those green. Okay? And we call these products, as you might remember. It's been a while since we've done that. Oops, product. Okay? So what I'll do here, and some people already follow this, is for this first subject, I'm going to multiply that first subject's deviate score from x, which was that minus 0.813 number. I'm going to multiply that by the minus 0.294 number. I think that's C5 versus G5 in terms of the cell addresses. Okay? And I wind up with a product of 0.2387 when I multiply deviate x by deviate y for that first participant. Who's okay with that? Did I lose anybody there? We've actually done it previously, but we hadn't done it in a while. Is that working for you, Nina? Yeah. Okay, really good. Okay, so now that we have that product, why don't we get all the products? Formulaically, they're all identical to each other. They all have that same spatial relationship. Now we have something like 32 products. These are the product of the deviates, the x deviate and the y deviate. And then we get to sum those up. That's what the summation sign means. So we'll drop down here. And we can, if you want to be fancy, click on this summation sign. Okay? And I come up with a 1.5725. Who can confirm that number? And why don't we just label that SPXY? I'll save that also. Okay, so I think we have now all of the ingredients that we can just begin mixing and matching according to our formula sheet. I will not require that you memorize this formula. If we do have this one on the final exam, I will hand you this formula. Okay? But I think you've probably worked with it enough that that wouldn't be too difficult for you to do. Okay? All right, so we have all the ingredients, and we were trying to find the best fitting regression line. We can also find the correlation, since those two are so similar to each other. So why don't we do this first? Why don't we see if we can compute the slope? So in column B, I'm going to write the word slope. I'm using row 41. You don't have to be there exactly, but I'm in B41. I put the word slope. And then can you help me out? How am I going to get that? Using this. Let's all yell it out together. The slope will equal SPXY. So I'm going to click on the 1.5725 number. That was over here. That's going to be my numerator. Okay. And then I divide by SSX. Okay. Real good. And I come up with a slope of 0.4325. Okay? Or it might depend on how wide your screen is there, but within rounding, who can confirm that number? Okay, is that working for us? All right, really good. A couple of ideas about that. If we were to take an R value right now, would it be positive or negative? If we were to take an R value, it would be positive, and why is that, Kip? Slope is positive. Right? So if we can think about, here's a scatter plot, right, and we have our best fitting line, and we know that it has a non-zero slope. It's positive. It's not a really strong slope, but it's greater than 0. So it would have to be at least a modestly positive R value. Who's following that? Okay? So this slope will always be indicative of the sign of our R statistic. Okay? Okay, so in y equals mx plus b, we need a slope. We also need the y-intercept. If we turn the page, okay, we'll get the other component in our y equals mx plus b. This is the y-intercept. We'll simply call it intercept. You like? Okay, and can you yell out the formula for me? Equals mean y, and that's now right here. That's over the meanie. Okay, 3.1 and some change. Okay, and then we subtract from that a quantity. We'll open a left parenthesis so we can keep our order of operations correctly, and we'll now click in the slope, which we just computed. That's immediately upstairs from where we are. Okay? And we're going to multiply the slope by the x mean, that's x bar, that's the 3.3125 number. And then we close that off. And there it is genotypically. I'll let you hit enter, and I'll let you call out the number that you get. 1.76 and some change. Okay. All right, and that works for us. Okay, so now we have the slope and the y-intercept. Okay, so now we're really making great progress. Why don't we just write out the equation? Okay, so here's the equation, and if we need to expand column C a little bit, that's fine. Okay, that might help us. And the equation will take the generic form of y equals mx plus b. We'll now slide in the slope for m, the intercept for b. So the equation might look like this. Y equals, we can approximate, and we'll say 0.433 maybe. Okay, 0.433 x plus 1.76, I'll call it 1. Okay, something like that. And if you round differently than me, that's okay. Okay? But y equals mx plus b, there's our slope, there's our y-intercept. Okay, so that would be the equation for the best fitting line. Pretty cool that just by doing these differences and a couple of simple products, we can compute the absolute best fitting line. First, how many people are following that? Okay? Any questions on that? Okay, I think we're okay. I think that works. By the way, what do you think it means to have the best fitting line? So, any way of describing the best fitting line, maybe even mathematically? Yeah, thanks.
I don't know. To me, it seems kind of like the general trend.
Okay.
So
Okay.
it doesn't maybe give you specific information, but like it gives you a general
Yeah.
direction.
Okay, it gives you a general direction. I wonder if I can draw that. So here's a sample scatter plot. Okay, and hopefully you can see there's an upward trend. The data aren't perfectly linear, but there's a general upward trend in that. Okay. Now let's say that I was going to try to tell you that here's the best fitting line. You would say, well, the slope's about right, but you've missed on on the y-intercept. Okay. And then let's say I did something like this. Well, maybe the y-intercept has gotten closer, but the slope's not quite right. Okay. So we want to find out what's a really good y-intercept for this data set. What's a really good slope for this intercept? Who's following that? Here's one of the ways that you could tell. And this is something we haven't mentioned before, but I think you now have enough quantitative reasoning savvy to handle how we can tell what the best fitting line actually is. Imagine that I had this line up here, and I wanted to make the claim that that was really the best fitting line. How might I go about doing that, claiming that this was a good line? Well, you might think that the best fitting line would be, if you will, closest to all the points. And clearly that line is not the closest of all the possible lines we could draw to each of these points up here. We could get a better estimate than that. One of the ways of quantifying that is to do it this way. I could say, how much distance do I have between that dot and the prediction? Okay? And I could get a y value and a y value here, and I could get that deviate score, and I could square that deviate. And then I could do that dot off of its prediction, that dot off of its prediction, and I can get all the deviations between the prediction line and the empirically observed data points. Okay, so I could have all these scores, and I can have the best fitting prediction, and I can difference those, and I could then square those differences, and I can get a sums of squares. This would produce a huge sums of squares, right, because that's way off. But if I had a line that was really nicely fitting, there would be one line that would actually minimize the sums of squares, right? It would still be greater than 0, the sums of squares, but this would be the line that minimizes that quantity. It generates the least variation from the empirically observed data points. Who's following that? Does that work for us? Yeah? I think I see a confused face. No? Okay.
No.
Okay. Okay. That's all right. It's a subtle concept, but when people say, well, that's the best fitting line, what does that actually mean? That's the line that minimizes the sum of the square deviations between the prediction line and the empirical observations. Okay? Okay. So that's just a little bit of background. We have this equation, and that's the one that does the trick for this data set. Okay, let's see if we can go just a little bit further, and why don't we get towards something that's APA style. And we'll see if somebody can call out how many degrees of freedom we have in this regression analysis. Not 2, but 2 is going to be an important number. So let's think about the degrees of freedom. They're not actually on here. Maybe you have to remember this from yesterday's conversation. 32 minus 2, that's where that came from. So let's all just remember that the df in this particular case will be equal to 32 minus 2. Okay, let's make sure we all understand where that came from. Who follows that? That's our formula. We had 32 pairs of scores in this data set, and we made one estimate for this mean, one estimate for that mean. 32 minus the number of parameters we're estimating. 32 minus 2 gives us 30. Okay? So in the world of APA, we might say that we're going to run an R statistic that had 30 degrees of freedom. Just a stretch? Okay. I thought that might be a question. Okay. All right. So that's an R statistic with 30 degrees of freedom. Oops. Don't need to have that. Okay? And then I can say that's going to be equal to, and we'll see if we can compute the R. A couple of ways of computing the R. Does anybody remember the formula for R? It actually isn't in front of you. You can jot it down here. The formula for R, and I wouldn't expect you to remember this, R is equal to our old buddy SPXY over the square root of SSX times SSY. Okay? Okay, so why don't we see if we can cook that one up here, and we'll figure out what our R value actually is, relating college GPA and high school GPA. Okay? So our numerator is going to be equals the XPXY value. Okay? I'll put in a space, and we'll get to our denominator. Can somebody call out the syntax for the square root function? SQRT. Okay, that's been a little while since we've done that one. And then we open a left paren. Okay, so we have that SPXY is our numerator divided by the square root SQRT. Kip correctly told, excuse me, SQRT. And then we're going to put in here SSX. And we're going to multiply that by SSY. Okay, so that should be that. And we come up with 0.3987. Who's got that? Okay, and that works for us. Let's do a check on that. Let's just do an R check. Anybody remember the syntax for checking the R? A couple of different ways of doing that. I'll give you the equal sign. Anybody remember which of the R's this one was? It's not the Spearman, it's the Pearson. Okay, so we can say equals Pearson as one of the ways of doing this. Equals Pearson. And we can highlight over high school GPA. I highlighted over the raw scores 1 through 32. Those are the actual values. Then I put in a comma, and I highlight over these scores. This is column F. So we're taking the values in column B and F. We close that off, and we wind up with, to something like 10 digits of precision, exactly the same value. How many people got that? Okay, thank you. Really good. So now we know that's the R value. Okay? All right, now here's one of our new tricks for today. How many people have the other handout that's the table? Okay? All right, so if you can grab that, I'll let you do just a little bit of investigation on that. Normally, we would like to, at this point, put in an equals RINV and figure out something like the critical value, or equals RDist. But why won't we do that? Because we can't, right? Because Excel didn't give it to us. I don't know why, but they didn't. So now we have to go back to 1993 when I was doing what you're doing as an undergraduate, and we have to look at a 1993 table, and we have how many degrees of freedom, did we say? 30? Okay, so can we go down our columns until we get to 30 degrees of freedom, and we can look over at, say, an alpha level of 0.05, which is what we use in this class. And so the criterion alpha level, I should say the critical value would have to be how big? 0.35. So we needed an R value that was 0.35 or bigger in order to reject the null hypothesis at the 0.05 alpha level. Okay? If it helps, I can draw that. The R statistic has more or less a bell-shaped distribution. And it ranges, as we talked about yesterday, from -1 to +1. Oops, +1. It's centered at 0. Our critical value was, what did we just say? 0.35? Okay, so maybe here-ish. Something like that at 0.35 is our cutoff region, and here is 0.35 again. Minus 0.35. Anything more extreme than minus 0.35 is going to generate a significant R value, okay, and we can reject the null hypothesis. So should we retain or reject the null hypothesis in our data set? We're going to reject because our 0.39 is greater than our 0.35. Okay, so we have a greater value. Now, of course, we don't get the exact p-value here because we don't have an R-dist function, but we can get one in just a few minutes inside of SPSS. Okay? All right. So that is our conclusion could be something like reject HO. Okay? Because we've exceeded the critical value. Okay, and now we have not only the R value, but we have the equation for the best fitting line. And there, you can imagine there can be variations on this that would have given us the best fitting quadratic function, the best fitting third or fourth or fifth order function. For those of you who remember polynomials, you can find the best fitting sinusoid, but we'll leave it at the best fitting linear equation. Okay? Any questions on that? Okay, why don't we do this? Why don't we do exactly the same analysis, but we'll learn how to do it inside of SPSS. This way, if we had a really, really big data set with maybe tens of thousands of data points in them, we wouldn't have to do all this manually. We can take advantage of that in SPSS. So I'm going to minimize this. Please don't put it away. We're going to need you to copy and paste the data. But we'll see if we can just confirm the numbers that we've done here manually. We'll see if we can confirm them in SPSS. So I'm going to open up that. And we won't need to open up a existing file. We'll put in our own data manually. We'll go to variable view, and we'll see if anybody can remind us how we might begin defining our variables. Kip's got it again. Okay, we'll do participant, and we may or may not have enough energy to put in P32, 32 times in a row, but that's the idea. And Kip, can you remind us what else we do with type? We go to string, and can somebody else tell us what string does for us? Allows us to use letters rather than just numbers. Most of SPSS is just filled with numbers because it's a statistical package. Sometimes you want to be able to label something with a name like P1 or P2 or Marin or Nina or something like that. So we can put in string variables. Okay? And then just to remind you over here, these were the variables that we were looking at. High school GPA and college GPA. So we need to add those to our SPSS variable list. Okay? And you can abbreviate this as you like. I'm going to put in HS and then lowercase GPA. You can do it that way or some other way. Remember that if you try to put in a space, SPSS yells at you. Right? It will say, hey, you have an illegal character there. Okay? So I'll put in high school GPA. I'll put in college GPA. Okay? And we'll leave those as numeric. If we wanted to be fancy, we could come over here, and we could say that these measures are actually scale variables. And what we mean by that is GPA is measured on a continuous scale that goes from 0 to 4 at Denison. There might be a different range at different schools. That's a commonly used scale. Okay? And then if we flip over to data view, you can see we have participant, high school GPA and college GPA. So we've now created a template into which we can paste our data. Who's okay with that? Any questions on that? Please. No, disagreeing. Okay, really good. Okay, we don't have to go all the way down, I think, but if we just wanted to see if our string variable was working, can we put in a P1 and maybe a P2, and we get the point. I wouldn't ask you to spend the next 3 minutes putting in the P. we could do that if we wanted to, but we don't have to do all that. Okay, why don't we go over to Excel and grab the high school GPA. Remember, that's in Excel, and it was cells B5 and on down. We'll see if we get all 32 of those scores. We can use a Control-C to get the ring around the rosy. Okay, there it goes with a Control-C. And then we can flip back over to here. We'll do a Control-V as in victory, and hopefully everything lands between the rows of 1 and 32. I think I'm in place. Every once in a while I mispaste. Okay, who's got that? Okay, we pasted from Excel over to SPSS. Okay, why don't we do that one more time? We'll pick up the other variable. This is our criterion variable, college GPA. This is what the folks over in admissions were trying to predict for each of you before you were admitted to Denison. Control-C gives us another ring around the rosy. Okay, that's in the memory buffer. If we go back to this side, college GPA, Control-V, and we'll see if I got it right. Looks like I've got 32 pasted, and we could put in all the P's, but not an effective use of your time. Who's okay with that? Any questions or comments, or did I lose anybody in the cutting and pasting? Yeah? So the other day in PowerPoint, we had showed you what the steps were for doing the regression analysis, and maybe you read about that in the book. Anybody want to get us started on this regression analysis? This regression analysis? Analyze? Okay, there you go. All right. Now here's that big menu again. Regression, okay, there it is, okay. Now this is a little confusing. Which one do you think we want to use? Linear regression? Okay, I think that could work. Binary logic. We could use maybe a few different ones. Why don't we go with linear? See what kind of trouble we get into. Okay. We are going to do the y equals mx with space, and that's looking pretty good. Which one are we trying to predict? Which one is our dependent variable? College GPA, right? So the folks over in admissions were trying to predict how you might do in college based on your high school GPA. We'll make that an independent predictor. Okay? Does that work for us? Who's got that? Slid those into place? Okay. And then we could look under statistics, and probably everything is checked off. We could click on descriptives if we wanted to. Maybe we don't need all of that, but we'll do that much. And we'll just say continue from there. I'm going to leave the plots empty for right now. Why don't we just go ahead to click on OK. So we'll get a regression on these two. Okay. All right, and we want to go down to the coefficients box. First, how many people got a coefficients box? You were able to get that? Does your coefficients box look like mine? Okay, all right, really good. So why don't we see if we can have you help me in developing what this equation is going to look like. Okay, so I know you already know the answer because we've basically done the equation in Excel, but where will I go inside of my coefficients box to build the equation? Okay, right, so unstandardized coefficients B. Okay, and can somebody help us? I'll give you a start. We want to predict a y-score equals 0.433, okay. So this is the slope, essentially, of the high school GPA, our predictor variable. We'll call that x for the moment, plus 1.761. That's going to be the constant, right? That's always what we get here, 1.761. Okay? So that's the equation that we got a moment ago. If you wanted to get fancy, you could even convert this just one step further, and we might say something like college GPA is equal to 0.433 times high school GPA plus 1.761. Okay. Who's all right with that? That work for us? Okay. Questions? Okay, a couple of points that haven't come up yet that sometimes do come up during the question and answer period. First, let's just see, looking at this standardized coefficient, Can people see that that number is very familiar to us, 0.39? Where did we see this number not too long ago? That was the R value, okay, right? Who remembers that we computed the R value? Within rounding, it's going to be that, okay? Okay, here's something that sometimes throws some folks off, so let's see if we can take a moment and cut off some confusion that otherwise may have arisen. And that is that the R value here relates the high school GPA to the college GPA, okay? And if we were to take high school GPA and put it on our x-axis and college GPA, this would be the R value. If we flip those two around, this would still be the R value. Who's okay with that? The R value doesn't care if I can anthropomorphize it. It doesn't care which is on which axis. It would still be the same. Okay? So far, so good? Here's where you need to hang on to your hats. You would get a different equation, though, if you flip these two around. The R value would remain the same. But if you now change the x-axis and y-axis variables, your regression equation could change. Okay? First, people understand that that could be the case, even if we don't understand why that's the case. Okay? That could be the case. The R will be exactly the same, but the coefficient singular is going to change. Okay? Or at least in principle it could. And usually it does. Just for fun, why don't we see if we can do that? Can we go back into SPSS and we'll just flip it around? So let's go, how did that go from the top? What did I have to click on? Analyze, then what? Regression. Okay. What kind of regression? Linear in the form of y equals mx plus b. So same variables, we'll just flip them top to bottom. We'll have college goes back to the list, high school goes back to the list. Now high school becomes the dependent variable. College becomes the independent variable. I'll let you catch up. You can hit OK when you're ready to go. I'll leave that there so people can see what we're computing. Okay, and we'll come down and we'll look at the coefficients down this way. First thing I'm going to point your attention to is the beta value, right, which is the R value, 0.399. How many people recognize that? Okay, so the R value didn't change. We flipped the axes, R didn't change. How are we doing on the equation? The equation now looks different. It's still the same structure, y equals mx plus b, but the b used to be 1.761. Now the intercept is 2.138. Or 2.139, 0.368 is going to be our slope. Who's following that? Okay? So you actually do get a different equation for the best fitting line depending on what's on what axis, even though the R value doesn't change. Okay? All right. Questions or comments about that? All right, really good. Why don't we do this? Why don't we see if we can generate now a scatter plot? It's been a while since we've done scatter plots. Does anybody remember? This might be like 3 months since we've done a scatter plot. Okay? A scatter plot is a graph. Okay, all right. Legacy, that looks familiar, okay. Scatter dot. I don't know why they call it scatter plot, but okay, that's what they do. And we can go with any number of these. Why don't we go with a simple one? I'm gonna pause there. I'll let you click on simple scatter and define. Okay? But that was, again, from the top. We went to graphs, we went to legacy, and then we went to scatter / dot. Apparently suboptimally named. Okay? All right, and then we can do something like this. We can go back to our original analysis, which is the folks over in admissions wanted to predict your college GPA based on your high school GPA. Okay? And just even doing that much, how many people have that? Okay, we'll click on OK. That'll be added to the bottom of our list. There it goes. And you can see that there's an upward trend-ish, even though it's not really, really strong. How many people do see an upward trend in that? And so maybe that's going to be like a 0.39-ish R value, and it'll be positive 0.39 rather than negative 0.39. Okay, so now we have a picture. We have the best fitting equation in either of the two directions, no matter what's on which axis, and we have the best R value. Okay, questions or comments on any of that? Okay, I think we're doing really well. Why don't we minimize this? Okay. And let's go back to Excel. Hopefully folks still have Excel open. People still have Excel. Okay, let's do that. Let's go over to Excel. And now we can learn some really neat tricks in Excel since we're just a little bit ahead of the game. Okay. Why don't we see if we can create a scatter plot inside of Excel? And to do this, we're going to highlight the two columns of interest using the control key. So we're not going to use the shift key now. This is the control key, which is underneath the shift key. And we'll hold down the control with maybe our left index finger. And then we'll paint over the 32 scores from the X column, which is our high school GPA. We'll hold down the control one more time, and we'll paint over the college GPAs. Okay? So that was the control key, and it allows us to now highlight two of them. I'm not sure we had used that before. Many people are able to do that. I lose anybody on that one? So that's the control key. And then if we go over to the insert menu, okay, the insert menu is way up top. It's maybe the second or third one from the far left, and you might see that there's a scatter. Okay? Yes, please.
I think you grabbed one of the cells and let's see.
Oops, did I grab? Okay, we'll see if that screws me up. Okay? We'll see if that screws me up. We'll go to scatter. Okay? And we can just take the first one here, and we'll see if I get in trouble. Yep, I think you're right. I got in trouble. So I'm going to do this. Thank you. It would take me forever. How come I'm not finding that?
Mine says some chart types cannot be combined with other chart types.
Okay, we'll see if anybody gets that. Do this one. Okay. Get rid of this guy. Okay, we'll do an insert, and we'll see if we get there. Maybe this won't work. Yeah. You know what it is? I've got a really funny range. I've got a range that goes from 1, so I've got a really, really small range here. How many people got a good-looking scatter plot? Anybody get a good one? You got a good one? Okay. I can't get a good one. Let's try that again. That one, and I'll do this one with control. Try to insert, scatter. There I go. Okay. I must have copied over something. So we'll do it that way. It might take you a couple of tries. Took me a couple of tries. But hopefully you can see that we do get an upward trend. It's pretty much circular, but it's a little bit oblong with a positive slope. How many people got that? Okay. You didn't get, okay. Okay, so some of us got that, some of us didn't. Let's try it one more time. Okay, let's try it one more time. And I'll get rid of that, and I'll show you what I did. Let's go all the way back to 0. So let's just put everything here in A1, and we'll start anew. Okay, everything's there, but nothing is highlighted at the moment. Okay, who's got that? All right, now let's just take a regular cursoring. We'll highlight over all of that. I'm going to take, oops, these guys. I want to take my GPAs from high school. Got those 32 highlighted. Who's okay with that? Okay, and then maybe I can do also a control, and I'll go over the college GPAs if it will let me. Okay, and we'll see if I have any luck this time, as I did one of those times. I go back to insert, scatter, and there it is. Did that work? No?
Sorry, I missed mine. How do you change the range again?
Okay, so we will start from scratch, right? Start all the way from scratch. I'll do it one more time. Help your neighbor if you're need. Okay, let's go back over to here. Katie, is that working for you?
Wait,
okay.
Can we just delete first?
Yeah, just get rid of the other graphs. We don't need those. Okay.
I need to delete it.
You click on it and hit the delete button.
There you go. It's not working.
Okay.
That's not working.
Okay, let's see if we can do this together. So let's all click on 2.5. First, is everybody's clear? Does everybody have a clear slate? Okay. Who's got 2.5 clicked? Meg, is that working for you? Do you have 2.5 clicked? Okay. Now, just as we normally do, don't hold anything down. Just drag over like you normally would, and we'll highlight those in column B. Okay, so far so good? Okay. Index finger, everybody. Okay. Let's go on to the control key, and then we'll go on to the 2.9. And we'll drag all the way down. So now we have two columns highlighted in blue. Okay, so far so good? Then if we go insert, and we go over to scatter, and we take the first scatter, we get that. Who's got that?
Is it because you pressed your control key on the first one that it gets messed up?
But maybe that was it. Yeah, maybe. Yeah, I actually did it both ways on my. I have a slightly different version in my office, and it worked both ways there. But it works this way here. Who's got that?
Mine's just a straight line.
Yours is still straight lines. Okay, so we'll come over and get that in just a little bit. Okay. All right. So there's that. All right. What I'm going to do is zoom out just a little bit. We're going to go to View. We'll zoom out, and I'm going to go out to maybe a 75 or something like that. So it's a little bit more visible. We can see pretty much the whole thing. Okay. Show of hands one more time. Who's got the scatter plot working? Okay. All right, let's do this just for fun. Whether your scatter plot is working or not, just for fun, why don't we see if we can now put in some random numbers here. So GPA ranges between 0 and 4. Okay, so just for kicks, can you all join me by going to 2.5? Okay, we'll put our item right there. You can hang on to your scatter plot if you have it. If you don't have it, you can destroy it. We won't need the scatter plot necessarily. Okay, and why don't we generate random numbers between 0 and 4, since that's what a GPA could be. What is that syntax? Wow, there they are. Okay, rand between. Okay, and we'll put in 0, 4, left paren. And so our first number, which might have been 2.5, gets changed to some number, and if we hold down the F9 key, that number changes randomly. Who's okay with that? We now have a random number in the first position. Did anybody not get that? Okay, looks like we're all there. Can we now drag that down, and we'll get a whole bunch of random numbers for these 32 people in column X. Okay, and then we hold down the F9 key, and all kinds of neat things happen. For those of you who have scatter plots, not everybody does, but all kinds of neat things happen. Yeah, they're all whole, okay, really good observation on Meg's part. They're all whole numbers because, anybody help us out? Yeah, so the rand between command only gives you integers between bottom and top number, okay? We'll come back to that in a moment. Can we do that one more time over here? Can we go to the college GPA equals rand between? We'll go with these very caveman-like integers of 0 to 4. We'll put it in for the first one. We drag it on down. Okay? And now we get a really boring plot. If you have a scatter plot over here, now it looks really boring. But if you hold down the F9 key, you get these raindrops on your scatter plot. And if you don't have a scatter plot, that's okay. You can just look up here and you get all of this. Okay? Who's got that? All right, that works. Okay, let's see if we can get a slightly more realistic now estimate of GPA. Still 0 to 4, but rather than just having these integers, what we'll do is we'll see if we can get some decimal values. Anybody have an idea of how we might do that? What does equals rand do? Has anybody played with it? We've done it once or twice, but not in a while. Equals rand, not rand between, but equals rand. 0 to 1, a whole bunch of decimals between 0 and 1. So can we go back over to our very first item, way up here. This is the first participant, high school GPA. And we'll say equals rand, left, right parenthesis. And we'll pause just there. We won't hit enter just yet. That'll give us a number between 0 and 1. If we multiplied that by 4, that would give us some number between 0 and 4. Who followed that? Okay? So if we multiply a 0 by 4, we get 0. If we multiply a 1 by 4, we get 4. So why don't we say equals rand times 4? Now we've got some number. Mine's a pretty unimpressive GPA of 0.33. It's hard to get into grad school with a 0.33 GPA. But okay, there's that. And then we can do this over here. Equals rand, again, times 4. And now our scatter plot doesn't look so much like the raindrops that we had a moment ago. At least we're getting more fractional values, decimal related values for those of you who are over here. Does that work for us? Yeah. Okay, one other thing that we might do, and we'll make this the last one. Let's just dial down to this bottom bit, and I'm going to zoom back in. You don't have to zoom in. I'm going to zoom in at 100, so people way in the back can see this. Okay? And what you might notice is that every time I hit the F9 key, I get a new R value. I'll make that in red so people can see it very clearly. Okay? And my particular R value here, minus 0.04, is not significant. What would it have to be for significance? What did we say? Has to be how big? 0.35. Okay, so why don't you just hit F9 slowly, maybe once every second or so, and after so many taps, you'll eventually get to one that is statistically significant, either greater than 0.35 or less than negative 0.35. Okay, I've got a 40 finally. Okay, right? And so if I now take a peek at that 40 and I look at my scatter plot, hopefully I'll see some kind of a trend there. It's at least a little bit upward, whereas if I'm just going randomly, it's pretty much a blob with no particular trend. Okay? Okay, we'll do it this way. We'll have everybody tap on this thing until you get to a positive or negative significant value. Can you do that? And hold up your hand when you get a significant value. There's a couple of hands. I'm going to do it too, till I get there. Oh, just missed. I'm trying to get to something greater than 0.35, just missed. So you can see how difficult it is to get to one of these numbers just by chance. There was my 0.42. 0.38, I got there. Who's got something that's significant? Okay, we're all right. Why don't we end on that note? Okay, so we all randomly generated a statistically significant correlation. You can see how rare that is. Okay? All right, you can save all that. In fact, I'll save that here. If you wanted to save that to your assignment inbox, that's fine. I've got it saved on the S drive. I look forward to seeing you Monday. Hope you have a wonderful weekend.